Hi. I know the homework is due tomorrow, but in the past 24 hours or so, I've gotten a number of questions from students about problem 7. And in particular, there seems to be some confusion about how do you even get started on this and what exactly the question is. So I've talked to a couple of students, and you know, I've come up with an analogy that I think sort of helped get the ball rolling if you're looking at it and just totally frustrated and stuck and don't know what to do. And hopefully this can help you out a little bit. So the problem says that we're going to look at some wave function, psi, that is equal to 1 over the square root of 2 times psi 1 and psi 2 for a particle in the box. Right? And so we're going to have v infinity at x equals 0 and x equal a is going to be equal to 0. Okay? And so remember, psi sub n is equal to square root of 2 over a times the sine of n pi x over a. Okay. So psi 1 square root 2 over a sine pi x over a. Okay. And likewise, psi 2 is square root of 2 over a sine 2 pi x over a. Okay. And the question is this wave function normalized? So let's take a step back and realize what we mean when we say it's normalized. Remember, the physical interpretation of the wave function, the probability distribution is a function of x equal to psi star psi. Okay. So in order to be a valid probability distribution, the sum of all the probabilities, or the integral of psi star psi dx, has to be equal to 1. Okay. If the wave function is normalized, this will be true. If the wave function is not normalized, then we need to have some normalization constant n such that in psi star in psi dx is equal to 1. Okay? So that's a little bit abstract. Let's do a really concrete example really quick. Okay? So imagine I have a particle in a box. And draw out a box. X equals 0, x equals a. And we're going to say that the particle has to be in the box. So imagine that I'm telling you that the wave function psi e to the minus 2x for x greater than 0, greater than or equal to a. Okay. Now this is not one of our special solutions, but maybe we can make a probability distribution out of this. Okay. So the way we would find out if this is normalized is that we would integrate psi star psi dx and see if that's equal to 1. Right? So in this case, integral e to the minus 2x e to the minus 2x dx integral, and take this over, integral from 0 to a minus 4x dx. This integral is pretty easy to do, right? So we have the integral of minus 1/4 e to the minus 4x evaluated at x equal a and x equals 0. Right? That would be the total probability of the particle being in the box. So we just simply evaluate these limits, and what we're going to get is 1/4 minus e to the minus a, e to the minus 4a over 4. And this is not equal to 1. Okay? So to normalize it, what we're going to do is we're going to say psi in e to the minus 2x. So now, if we integrate this, psi star psi dx n squared 1/4 minus e to the minus 4a over 4, right? We're just going to pull that n out. So psi times psi is n squared e to the minus 4a. Pull the n squared out of the integral. And we just saw what that integral is. Okay. Now we're going to force this to be equal to 1. So then we can write n squared equals 1 over 1/4 minus e to the minus 4a over 4, and n be equal to the square root of that. In other words, the following wave function, psi equals square root 1 over 1/4 minus e to the minus 4a over 4 times e to the minus 2x for x greater than 0, greater than a, or less than a. This would then be a normalized wave function, and if we summed up all of the probabilities that we would get from taking psi star psi, we would get 1. That's what it means to be normalized. That's what I want you to do for this wave function, for the wave function in problem 7. The other question that I've gotten is you need to calculate the average momentum, the average position, and even the average energy. And so just to rehash what we did in class, the average value of any operator is going to be equal to the integral of psi star O psi dx. And that's how we define the expectation value. So that will work with any operator, whether it's x, p, even the Hamiltonian. We define it to be the same, to use the same technique to measure all of them. All right, that's all I have. Hopefully that is a little bit helpful. And I will see you all in class tomorrow.